Mr. Giulio Guerrero will be the first, Giuseppe Orlando will be the first presenter, and the presentation is titled Entropy-Based Recurrence Diagnostics for Chipping Points in Complex Dynamic System, Evidence from Cryptocurrency Markets. So you have 15 minutes for the presentation, and we will have 5 minutes for questions. So go ahead.
Okay. Thank you very much. Okay, thank you. But you start from the outline? Okay, this one. Okay, so this is a joint presentation, and then I'm the presenter. And then I have done this work with a colleague that is Julio Guerrero, that is a physicist. So the idea was to understand whether we may have something to say about entropy and the time series. In this case, about financial markets in cryptocurrency. But what we are going to present today is more general in the sense that it can be applied to any time series. Okay, so what is the beginning? We start from some common issues that if we analyze time series with normal standard statistical tools, we cannot identify some characteristics of those time series. So first order, second order, whatever, statistical tools are not able to tell us again, what could be the real structure of those time series? So the idea is to introduce recurrence entropy framework. And so we combine entropy, that we'll see later, with the recurrence plot. And then the idea is to identify the structure of the time series plus what we call tipping points. So in physics, you may call change of phase or whatever. And then, well, why we need that? Because we have noise. And sometimes we cannot distinguish between what is the structure and what is noise. So this is the process. So we start from a time series. Then we take tokens. We find the embedding and the delay and tau. And then we apply to that recurrence plot. We build histograms. And then we compute the Shannon entropy as well as the linear entropy. And then, well, I've been told that I have just 50 minutes. Maybe we can, with the question session, we can discuss with more detail what we are doing. But essentially, here we talk about probabilities. And here is kind of X-ray of the time series. So what we are going to do then? Well, this is the Shannon entropy that I've been told today that has a long history. It's not just Shannon. I didn't know that. So it comes from Boltzmann and so on. But at the end of the day, this is probability. And then we have this recurrence plot that we said before. Essentially, a recurrence plot is a plot that shows how close in a dynamical system, so a time series, for example, how close the next point is to the previous one. And then, well, the period in which we have something close or not is what we said, the delay, the tau that we have seen before. So essentially, we have diagonal lines in the recurrence plot, and then we count occurrence, and then occurrences. So, and then we get an histogram for it. And then this is the probability of distribution. And given that, we compute the entropy. And then, well, this is the interpretation. So we know from this process what is the probability of observing something that is deterministic or is not deterministic, that is recurrent or is not recurrent. And then, well, with low entropy or high entropy, we can distinguish whether something is predictable or not, if it's more likely to happen in the future or not. So essentially, the entropy is the measure of uncertainty, but that is from the probability distribution of the histograms that I mentioned before. And then, well, what we do? We can take short rolling windows. We establish a threshold. So we said before that recurrence plot, I will show you later a picture, is how close in time is the next point of the time series. And then in order to measure that closeness, the boundary, we have to fix a threshold that in this case is at 0.1 sigma. So if it's within this limit, next point we say that is close. If it's outside this limit, we say that is not close. And well, we already mentioned this. And now I want to show you an example. I take a Gaussian signal, and then I change the mean and the variance, just to shock, and to see whether this approach is working or is not working. And then, well, we can see through the recurrence plot that is we can see from the recurrence plot that, as I mentioned before, is kind of X-ray of the time series, whether we have structure in the time series. And then if we can highlight transitions. We said before tipping points, we said change of phases, but essentially that is the idea. So let's have a look. This is the time series. And then this is a change point that is common to find in statistics. I applied what is default in MATLAB. That is a Lavielle method.
Well, this is the baseline in red?
That is a change of the mean.
What?
Change of the mean. And then if you see, the difference is not only the mean, but also the variance. I change the mean and the variance. And then if you use what is called Lavielle tipping point identification, and this is standard in MATLAB, but also I have published a paper about how to identify a tipping point or change in the structure of a time series that I can share with you later if you want. But essentially, this is the default. I use the MATLAB default, as I said. And then I have taken Gaussian signal, as I said, and then I shocked. I shocked in different periods. I used a different mean and a different variance.
And where is the transition in penalty?
Well,
Is ask the question after? Oh, okay.
no, but these I can answer. So you see, here there is a change point that highlights that you have a different mean. But then, again, I changed also the volatility. So you can see that here the volatility is lower than here. Okay? Good. So if you say, if you take the signal, you can see so much. And then the recurrence plot, when you see a dot, it means that, well, you have a point next to the previous plot. But if you take the variance, well, you see a clear structure, a change of structure. So, as I said, you can use this as an identifier of the structure of the time series. And then you will see that here, because the mean is smaller, the dots are closer. So it's more predictable. And instead here, you can see that the distance between points are bigger. And you can do the same. You can apply this technique to check the diagonal as well. Sorry, what is it? Okay, as well as the vertical or the horizontal line, because it's symmetric. If you see this plot is symmetric. So either you focus on the diagonal and the horizontal line, or diagonal and vertical line. It's the same. Okay, and then I have taken Bitcoin data, so daily data. I cannot show you the full analysis, but just to mention that, well, we may apply this technique to that time series, and then we can find that we have a clear identification, clearer identification of the changes if we apply that analysis to the variance. And instead, what I want to show you is a market crash intraday. So we take intraday Bitcoin data, and then we can find in this daily data 3 tipping points. And I show you the time series. So you see, this is a crash. So first there is a crash in the market, then there is a stabilization, then here you can see the recovery, and here the normalization. So you can identify in the time series 4 points, 4 areas. And so you see here you have more dense recurrence plot, and the same here. So this is more or less, as we said, more predictable. When is stable, no? But then, when you have high volatility, you can see that, for example, in this case, the predictability of the time series is more complicated. And, well, these are the data regarding the embedding and the delay. And essentially, we have denser neighbor, short diagonal in the first part, then lower laminarity and more of diagonal structure. So after this, so we have a crash here, as we mentioned. And then reorganization, and then relaminization, but with persistent fragmentation. So normally you cannot see that with statistical tools, but thanks to this technique, you may understand better what is going on. And then, well, this is the information diagram. So we have plotted the linear entropy and the Shannon entropy. Thank you very much. And then if you do that on the diagonal, on the signal, well, you don't see very well. But here, if you plot the diagonal lines, the variance, you can see that this is the 4th period. this is the second period, and the highest is the first one. So exactly when there is a market crash. This one. Okay, so what we said, this is interpretation, you already mentioned, we don't have so much time, just 2 minutes we said, even less. And then these are the results, and then, well, they are in line with what I described. And the last thing that I can show is about the return volatility regime. So if we divide the time series according to this return volatility, return versus volatility, you can see clearly that there are different periods, regimes. And those regimes are the ones that are highlighted thanks to this technique that we have proposed. And then normally in the financial literature, they say, well, when you have a crash, you have more directionality, and then the entropy should be lower. But if you take the volatility, this is not true. So again, you apply this technique to the volatility, not to the time series. And then again, you can see clearly the structure of the time series. Let me skip all this discussion. So, the method is model agnostic. There is no more. That is effective when we have these short windows. We can interpret physically this the results, and then it is resilient to noise. And then the last thing, if someone is interested, I'm editor of a special issue in mathematical finance theory methods application. If someone is interested, well, you can send me your paper. Thank you very much, and I'm happy to answer your questions.
Thank you, Professor Rondo, for the talk and the interesting presentation. Thank you for this presentation and your talk. And if you have any question, please.
Sorry, but could you explain us or me here the embedding? I'm curious about the more details.
This is not. This is a standard from Takens.
Yes, it's a standard, yes, but you know, it's how many series, what kind of time?
I just take one.
Yeah, this one,
for example.
Yeah.
Let me go
and
back.
how many embeddings you do, and what you discard, and
well, there are techniques in order to find the optimal embedding. That I use them.
You use one series?
I take the one time series.
Yes.
And then I try to find the right embedding.
Okay.
And the right delay.
Okay. Yes.
There are techniques not developed by me, standard, that are doing that.
But there is the old Takens theorem.
Exactly. Yeah, exactly.
Actually, my question is related to this one. How your results are sensitive to this embedding parameters, so M parameter and tau parameters. You try different one, or you just fix this?
No. Is not sensitive to that because we tried several. Let me show you this one this one, for example. We tried, for example, for prices was stable, but for variance we found two cases. So this is the embedding, and this is the delay.
Okay,
and we found similar results, and we did many trials, and more or less is stable. And we used, as I said, daily data plus intraday data.
I'm asking because I was playing with this RQA analysis a long time ago. And the second question, can you make any predictions based on these measures? For example, on laminarity or determinism, because usually the direction is after the crash, yeah? So you can't make predictions before, or they are just after the...
Well, prediction, maybe is mentioned somewhere, is limited in the sense that what we have done is when we got the complete time series. Okay? But, if you are here, for example, or, I don't know, here, and you have run this algorithm, more or less you know that it is more likely that the next result will be close to the previous one.
So you can.
Well, you can say that more or less you are there, but you cannot, is not, what is it, a statistical model that you can, with a given probability, even though we do have probabilities, you can stay there.
Okay.
But yes, when you are here, more or less you know that is likely that you will be there unless something like a crash will repeat.
Yes, the next.
Actually, I wanted to ask something related about this embedding dimension. Somehow it astonishes me that that n equals 3 is sufficient, because it is many-dimensional dynamics. I wouldn't expect something like 6, 7, maybe 8. And second, related, is how do you determine this delay time? For the financial markets, the memory drops down immediately. So one.
Well, regarding the embedding, there are many papers, and also some of mine, that show that in finance, in economics, you have low dimensionality.
You try to relate it to the Takens theorem?
Yes. You can find low dimension chaos in finance or economics. And again, it's not me, I published also on this, but I'm just follow the unestablished literature. And regarding delay, well, not so much. You don't have so much delay, because more or less you may revert to the previous. You may have a stable time series and like this. More or less is stable. More or less here is stable. Not exactly, but is stable. So you may have not high lag.
Thank you, Professor.
Thank you.
The next presentation is complexity characteristic of natural language. This is the role of continuation. Presented by Stanisław.
This is the last. So we have to. No. No. You see, I have so many slides, so much material that.
Whatever means
I was working on reducing it to maximum, so I can at most, maybe I don't need that one, it makes more noise than, I speak loud.
We need it for the
I see.
recording. Thank you
Okay.
so much.
No. What is the first one? Oh, as you can see, it is also related to entropy. See? For this reason. Thank you. There are actually many reasons to talk about the natural language. First of all, we wouldn't be able to conduct this kind of a conference with no natural language. But the even more fundamental reason is that that actually the nature, the universe, that we definitely would consider complex, created the natural language. It's an amazing, and very, very puzzling thing, how did it emerge in this context, because we don't understand. Actually, it's, the most common thing and we know least about. What was the beginning of natural language? No fossils, no documentation. There are some estimates that it emerged some 100 years ago, 50, 100 years ago, and then slowly, some 2,000, 3,000, 4,000 years ago, it was converted mapped into the sequence of characters, so there was writing, and punctuation is a relatively recent achievement, let's say. Something like a couple of 100 years ago, before people didn't know. It's sort of astonishing. It seems so natural to us, right? But it was this recent, so the spatial role of punctuation. So that since language is created by the world, by nature, which itself is complex, so it should also carry the characteristics of the same characteristic, the characteristic of complexity. And also, since nature is astonishingly mathematical, it's so well described in mathematical terms, you don't fully understand why. But even if some equations produce solutions that seem, initially with no physical interpretation, like Dirac equation predicted negative energy solutions, which was considered an artifact, turned out the positron. Black holes in general relativity and gravitational waves, the same story. So let's come to the natural language. Why natural? We understand, we know. The general signatures of complexity, the scaling laws. Fits to many other concepts related. Long-range correlations, fractals and multifractals, applicability of complex networks, concepts. Which ones apply to natural language? One of the well-known is the so-called zip flow, which says that the frequency of words is inversely proportional to the rank of the word that it occupies in the text. So which means how frequently. The most frequent word is rank 1, the second frequent is word rank 2, and so on. So it is this typically plotted in the log-log scale, because in the log-log scale we best see if something is power low. So this is the original plot by Zipf, published in 1948 in a book, but he had it already before. Actually, Jean-Baptiste Stoup had it already in 1916, but he didn't interpret it so deeply as later on Zipf did it. Well, we did on our own some study related, but interesting in itself, but I have no time to talk about. What is characteristic on this level, if we count words, is that typically, something is this. Here it is not seen. So there is this bend down here in the beginning. It's whatever text you take, it's, what is it? Is it defected or I am defected? Maybe, well, yeah, that typically bends down, and even Mandelbrot introduced such a correction here, so that to account for this bend down. Now the question is, as you may remember, I promised to emphasize the spatial role of punctuation, this most recent innovation. It turns out that actually another reason for looking explicitly at punctuation is that we heard today a lot about large language models, the architecture that conditioned the success of large language models is this transformer architecture, spatial kind of multi-layer neural networks with long-range memories introduced. And what is characteristic conditions its success is that punctuation is introduced in an equal footing, as equivalent to words. In that, actually, the documentation that it makes a lot of sense on a more fundamental level comes from this paper published even earlier than transformer was introduced. This is my name, and these are all my students actually. That if they not only, the punctuation marks not only fit, align with this original zip flow, but even improve the scaling. And this dip that we had in the beginning somehow is sort of removed. Something like punctuation constitutes this missing part, of our language. So this is one thing important. Just recent study which shows similar effects occur in Chinese language. Yeah? They do. Actually, it's a very tricky thing for an independent talk. I could talk for a long time, They actually introduced already a similar way to Western European languages. They do, but they also have a trace of the older way, Somehow punctuation is incorporated in the system of character. Not fully, but to a large extent. This we experienced, Yeah. So it does, and now the question is, zip flow, this sort of scaling, is the one of the simplest ones. Does not carry a lot of information. Does some. It actually, I didn't point this out explicitly, but it works differently for different parts of speech, for instance. So not fully trivial, as some people were trying to supply such, interpretation and explanation of this effect. But if we, for instance, have a book and we permute the words in the random way, that just shuffle them, then the text, this shuffled one, obeys the same law, because the frequency of words remains the same. So this kind of correlations is not present in the zip flow, in the zip plot. So let's look at something more demanding. So since punctuation plays a spatial law, some arguments will come in the following. Let's look at the interpunctuation distances measured in terms of the number of words. So how many words are in statistical terms between two consecutive punctuation marks? Any, all maybe, The natural distribution to look at is this Weibull distribution, this one. We just maybe don't look at this. This is in a discrete representation. It's not very transparent. It's more transparent in the continuous representation. And in the continuous representation, it is a sort of a generalized exponential distribution. It's either stretched or complex. Complex depending on there are two parameters, this parameter and this parameter. And this parameter is, describes what is the degree of compression or stretching relative to the exponential distribution in rough. And now it turns out that the text, we did such study for 7 European languages, the ones most popular with many books awarded the Nobel Prize in Literature. And it turns out that they quite universally obey the Weibull distribution. The Weibull distribution is the one that is often used in the survival analysis. In what is the distribution of a lifespan of living organisms, or in the material sciences, how how long it survives the material under the pressure of stretching, for instance, like the spring, for instance. And many similar. So here the situation is sort of similar, because when we talk or we conduct our, thought, in our brain, or when we speak especially, from time to time we need to make a break, right? Because our breathing system demands that. So we have to somehow interrupt it, you know. So if the string becomes too long, we cannot afford it. So may have to do, and it really beautifully does so. So to make the long story short, it is so that if we take all the punctuation, then the viable distribution works very well. If we take only the full stops, the ones that end sentences, like period, exclamation mark, question mark, and ellipses with multiple dots. There are not many typically, then it doesn't work so well. But what is characteristic is that within the given language, the two parameters of this distribution look sort of only two of universal, but they differ among different languages. So they segregate languages, like illustrated here. So different for languages, and even if we translate the text from one language to the other, then, of course, we are talking about the professional translations. Then it points towards the target language. So it's a really strong constraint. If we now, it's interesting analysis in terms of the hazard function, which is equivalent in terms of parameters to the viable distribution. You know, it describes how urgent it is to put a punctuation mark if there was none so far. So English is somehow, and Spanish, little bit above, the least demanding in this sense. You know, this is, one can speculate for what reason. We make an interesting discussion, but we have no time for this. For Chinese also, but for Chinese the distances are typically, the parameters are much, correspond to much compressed lengths of sentence, of intervals. With the sentences is the last issue. Because the question, if a writer puts a comma or a full stop ends the sentence, is a matter of style or a matter of taste, you know, but something has to be placed. So on the level of the distances between the full stops, which means on the level of the distances of the lengths, sentence lengths, on the level of sentence length variability, you have much more freedom. And here, many more interesting effects we can observe. For instance, you know, when we look explicitly at the length of sentences, then it looks sort of rough, very rough. You know, it involves this, in financial terms, volatility clustering. You know, this is one of the books, but there are many more are like this. And when we apply the methodology of multifractality, then this one, for instance, which is feeding it involves this element of self-similarity, which means if we take a portion, magnify it, then we see this. If we take a portion of this, magnify it, then we see the same essentially. So this is the essence of fractality, and in general term of multifractality, which involves the whole spectrum of scaling exponents, and this is in fact the full glory complexity. Thank you.
For the talk and the interesting presentation. And if you have any question, please. Yes.
Thank you, Professor, for this presentation. I have just a curiosity. Have you tried Arabic?
No, not yet. If you can help us,
I have a very...
you know, we will be happy.
I have a very concrete example. There is a scholar.
Or we can make a paper in collaboration.
Well, I don't know if I'm competent for this matter, but the idea is that there is a scholar who made a number of marks in the Quran so that people, when reading Quran, can start and finish it the same way.
Yes.
Yes.
No.
Yes.
So I mean, there is a lot of data about this, and these marks help people here in Morocco and in the Maghreb in general to recite Quran, and they all know where to stop. So this is Habdi Waqf. So this is a good example in Arabic with the Quran text. So with these marks that help breathing.
Absolutely.
So-
we did study the Bible, you know, the Old Testament version, the New one.
The original in Greek?
Actually, there are not many books that develop this multifractality. Not many. They typically, like the Finnegan's Wake by James Joyce, you know, there is some Rayuela, but not many. You know, they all they are multifractal, and they all are considered to belong to the sort of literary stream of consciousness. Or,
That was going to be my question, because I haven't read the Bible, but my wife at some point said, okay, I need to read this. And then the surprise was, this seems like an endless bubbling, like a stream of consciousness. There is no, it sounds like someone desperate without ever finishing. But she was reading ancient versions.
Calculation shows.
Before.
Calculation shows that the Old Testament is more multifractal than the New, which means it must, explores more dimensions, so to say, in mathematical terms.
She was looking at the Greek version of the New Testament, like the first version was Greek. And the surprise was exactly this, and now I realized there are no punctuation. They never stop. They seem desperate to go on and on. And the reason is this, actually. And now I understand.
Read our papers or talk to us. That's all. And the proverbs, especially here. Speech is silver, silence is gold.
So why the Old Testament would have a more structure, more punctuation than the New?
Because
More centuries
by God inspired.
No, it's just like there is, because there are more centuries of writing and reading and something.
No, more centuries doesn't have been this way. Just the opposite. It will introduce more noise, and noise is mono, it's boring.
But through the centuries, someone may have...
There is a book. We studied the book.
Okay.
There is the longest novel ever, romance,
Yeah, which was...
Achtamenu le Grand Series. Something, 3 centuries ago. It's not clear who is the author. There's probably no one single author. There are many authors. There's a group of people, just dancing, swinging, drinking alcohol, and who, had time was going to continue writing. And that one is just absolutely boring in any respect. It's just white noise in this sense.
The Gilgamesh, are you aware of the first, the Epic of Gilgamesh, the first known?
No.
Look it up, it was written in the city of Uruk. It was about King
What?
Gilgamesh.
Say again, what?
Gilgamesh, I have 4 pointers.
I guess it's similar.
Well, yeah, it
We're
became,
talking to people.
but this is the city of Uruk. This is the city of Uruk, not Uruk. And it's the epic of this king, Gilgamesh. And precedes the Ark of Noah and all that.
And our question for this
You have a
presentation.
question.
Just a curiosity. Did you try to check the white space?
What? White?
Space.
White space.
White?
Space.
White space. The distance between white spacing.
White space.
You mean the length of the words?
Well, how many?
The distance between everything here is measured in terms of number of words. So the distance between spacing would be some one units, right? So not much interesting.
To see how many you have in a sentence. And if that is recurring, if that is fractal or not.
The same, the spacing is the number of minus 1.
Yes.
The number of minus 1. So it would be basically the same. But we did so.
Thank you very much.
Thank you, Professor, for the presentation. The next presentation, filter amplitude, dependence of correlation dynamics in a complex system, presented by Marcin. Yes. 12 minutes, please, for this presentation. Thank you.
Okay, so hello everyone. In this presentation, I want to show you how you might decompose networks based on cross correlations to extract various information. There will be an example from the cryptocurrency market, but actually you can apply it to many complex systems whenever you have time series and interactions between many entities, let's say. Okay, so I will start with the minimal spanning trees. Probably you heard about this. If not, I will just quickly introduce it. Then I will generalize it to add two additional parameters, Q parameter and S parameter. We talk about what they actually mean. There will be some examples from the cryptocurrency market and some dynamic changes. Okay, so minimal spanning tree, yeah? So you have full network, yeah? First you have correlation matrix, right? You have, let's say in this case, some cryptocurrencies. You measured how they are correlated with each other using Pearson correlation coefficient, so far nothing new. Then you are calculating the distance, yeah, because you need to have the distance measure between two nodes, and actually the edge white between two nodes is this distance, right? So if you have full network, everything is connected, every node is connected with some weight equivalent to the correlation coefficient. And then minimal spanning tree. Yeah? Minimal spanning tree is a structure, is a graph when each nodes are connected, but you have no loops, and you are minimizing the sum of weights. So in principle, in the minimal spanning tree, only strongest connections persist. If you use some prim or Kruskal algorithm to whole network, you will receive something like this. And here are the links which only remains. Here you have the full network, minimal spanning tree, and the links which remain. So actually this method can decompose the whole correlation network to simpler one when you only strongest connections persist in the structure. Okay, and we are using not the Pearson. I don't have much time, so I will just briefly talk about the method because here there was constructed, the minimal spanning tree was constructed by using Pearson correlation coefficient, and you are using so-called degenerate cross correlation coefficient, which have two additional parameters. The method is based on the trending. Maybe you heard about Hertz exponent, which is calculated by DFA, the trend fluctuation analysis. Something similar. In the essence, you have this exponent, the trend cross correlation coefficient, when this is parameter Q and parameter S. It works like this, that S is the scale, so you can choose on what scale you are measuring correlations, and Q parameter actually plays an important role because it amplifies or suppresses the variance, right? Here you have the mean variance, and this parameter Q, so you have large fluctuation, it actually amplifies the role, and if you have small fluctuations or small variance, it actually suppresses it. So basically this coefficient can measure the correlations on the level of high fluctuation or a small one. So you can treat it as generalized Pearson. It had the same properties, so from -1 to 1, the same properties. Okay, few words about cryptocurrency market. There was Bitcoin already, but of course there is no only Bitcoin. Actually the market, the whole market of crypto, there are many cryptocurrencies. It depends how you count them, because it's quite easy to create token, but it's harder to make some value of the token. But it's assumed that there are more than 10,000 tokens which are traded now. But actually, the Bitcoin has almost 60% of the total market capitalization. Second one, Ethereum is 11. If you take top 10, in terms of capitalization, they have 90% of the total market cap. How big is the market, right? So I updated it yesterday. So that was 2.5 trillion US dollars. So 10 power of 12. It is comparable to Amazon, right? Amazon is 2.7. Actually, the largest stock company now is Nvidia, is 4.8 trillion US dollars. So quite a big market. So there are many cryptocurrencies, right? So we are interested to measure cross correlation between them, right? So we took 140 cryptocurrencies, data from the Binance exchange. That was tick market data, 1 minute sampling in this period. And we calculated this coefficient in running windows, and then this distance matrix. And then from this distance, we calculated the minimal spanning trees, right? So, an example, if you take the full period, right, from the 2021 to the 2024, and construct minimal spanning tree, actually not much interesting because you have Bitcoin, which is the node with the most connection, or Ethereum has also similar amount of connections with other cryptocurrencies, right? So these are two highest capitalized cryptocurrencies, so actually you can expect to have such results when you take full period and use Pearson coefficient, right? So far, not much interesting if you consider full period and Pearson coefficient, but now let's move to apply these QMSTs, right? So we have these two parameters additional, Q equals 1, so Q equals 1 doesn't amplify or suppress the correlation, so you are averaging the role of the correlations, and the scale equals 10, so 10 minutes. And here you have two examples, two rolling windows, first one from April, second one May. That's actually crash. These two periods are taken in purpose because there was actually a crash in May 2022. So this one is before crash, and this one after crash, so completely different structure, right? Here the Bitcoin is central node. Almost all other cryptocurrencies nodes are connected to Bitcoin. Afterwards, the structure changes, right? So the network is clearly less centralized, even decentralized. These are two minimal spanning trees for the same parameter, Q equals 1, S equals 10. If you perform such analysis in the rolling window, right, you can see this break here. Here is the maximal number of degree, right? So here the Bitcoin has maximal number, the node with the maximal number of edges. So this value is actually the number of connections for red one with Bitcoin, blue one for Ethereum, and so on. Here the Bitcoin is dominating, right? You see the Bitcoin has the largest number of connections. Here is this May 2002 break, and afterwards the situation changed, so no cryptocurrency is dominating. Interestingly, here you have average path length. Average path length is the measure which actually counts if you start from this node, how many steps you have to this one. Yes, on average, on your averaging, how long it takes you to take from one cryptocurrency to another one. Yeah. So if the network is centralized, all connected to one, the average path length is 2, 1, 2 steps, right? If it's decentralized, it's more. So the measure is also fluctuating here. Here the network is more centralized, this break, and less centralized. This led, of course, to eigenvalues. So here the correlations were higher in this period, here lower. Okay, but this is the picture for Q equals 1. So if you don't distinguish large or small fluctuation, you treat them on the same level. And now we apply the Q equals 4. So now the large fluctuation are amplified. So the large one, the most interesting, right? Because when there are big moves on the market, you are actually taking profit or taking the risk of them. So here the picture is clearly messy, right? So there is no one cryptocurrency, as in this case when Bitcoin could be distinguished. here there is really mess. So no single one is distinguished. Also, the average paddle is significantly higher, right? So the network is clearly less centralized. Also, the correlations are generally lower. But here you can see some jumps, right? Jumps when the average paddle is actually higher. In the case for Q equals 4, so high fluctuations, than for average fluctuations, right? Also, there are some spikes in the eigenvalue, largest eigenvalue, so the correlation will clearly higher. It's interesting why in these rolling windows the correlation were stronger, and they at the same time they make the minimal spanning tree structure completely decentralized. Yeah. Here are two examples, right? So here is the same rolling window ending on October 2021, Q equals 1, so Bitcoin, Ethereum, two most dominant nodes. If you take Q equals 4, the network structure is clearly more decentralized. Another example, maybe even better, Q equals 1, the same January 2024, Q equals 1, so average fluctuations, and the network is more centralized, and here is completely decentralized for large fluctuations. We wonder what is the reason behind that. So why in some rolling windows the correlation are stronger for large fluctuations, and they make the minimal spanning tree structure completely decentralized. And it happens, which is related to this, to measuring these breaking points. Actually, these two windows, some flash crashes happened, right? Here is flash crash when the scale is small, but here are minutes, right? So here it happens in the matter of 5 minutes. So there were the price of all 140 currencies fall immediately, and that's at the same time everything was correlated strongly with everything, which produces such effect like here when no cryptocurrency can be distinguished, so there are very small differences between correlation. Everything is strongly correlated with everything. There are small differences, no other can be distinguished. To summarize, when you can use it and how, anywhere when you can actually have some time series and can construct a correlation matrix, you can apply this methodology, and when you can use it potentially, which we are now thinking about and working, to some kind of portfolio construction, right? Because maybe you know this famous Markowitz theory of portfolio construction. When he uses only simple correlation, you might generalize it to taking into account the correlation between high fluctuation and small fluctuations. Advertisement. We are running the special issue in the entropy, so you are welcome to, if you are interested in the cryptocurrency market, cryptocurrencies, so to add some contributions later. Thank you for your attention.
This presentation is presented through a video. No questions, just videos.
My name is Tomoko Sakiyama from Soka University. Today I would like to talk about this title. First, I will briefly introduce the overview of this study. In this research, we extend the game of graph to better control long-term dynamics. We propose the pause model, which introduces probabilistic stopping recurrence. and further extended it to the twisted model with state-dependent update rules. We then analyzed its evolution and spatial patterns through long-term simulations. As a result, we observe power of behavior indicating complex system dynamics. This model demonstrates the ability to sustain and even reactivate activity over time. Here, we would like to explain what a game of life is. So as shown in this figure, it is a type of cell automation where each cell changes its state based on simple rules, like follows. And we can observe how patterns evolve over time. As you know, there are 4 basic rules. The pass, if the cell has exactly 3 live neighbors, it becomes alive. And survive. If the cell is already alive and has 2 or 3 live neighbors, it stays alive. The third one is isolation. If the cell has fewer than 2 live neighbors, it dies. Finally, overpopulation. If the cell has more than 3 live neighbors, it also dies. Thanks to these simple rules, the OL can produce the complex patterns. However, in the case of the game of life, the system tends to reach a steady state after a while, as shown in this graph. This behavior occurs because the rules of game of life makes it easier for the number of living cells to decrease rather than increase. To address this issue, we introduce some modifications to our model. Here I explain the objective and the experimental setting. The objective of this study is to investigate the criticality of Conway's game of life by introducing the concept of peer pressure. For the initial setting, we use a grid of 100 by 100 cells with periodic boundary conditions. The initial density is set to 0.5. In each trial, we simulate up to 1 million generations. Next, I'll explain an overview of the proposed models. First, the pause model. In this model, we introduce a new parameter called the stop rate, denoted by P, for each cell. This value is updated based on peer pressure, and it affects whether the cell updates its state or not. The second, the test model. This model builds on the pause model. When certain conditions on the stop rate are satisfied, an additional mechanism is introduced, where a cell behaves in a constrained way. I will explain a little of this model in the following slides. Here I will explain how the stop rate P is determined in the pause model. We introduce 2 variables to capture the update dynamics. The first is interval run, which represents the number of generations since the last state update event. The second is interval pause, which represents the number of generations since the last pause event. Now we adjust the stop rate P based on the relationship between the cell and its neighboring cells. If many neighboring cells have performed update events while the cell itself has not updated, we decrease the stop rate P. In this case, P is defined as 1 divided by interval run. On the other hand, if many neighboring cells have not updated, while the cell itself has updated, in that case, we increase the stop rate P. Here P is defined as 1 minus 1 divided by interval pause. Finally, to evaluate the inverse of neighboring cells, we introduce a majority threshold. In this study, the parameters are set to 3, 5, and 10, and each case is analyzed separately. Here I will present the result of the pose model. We conducted simulations using majority of neighborhood thresholds of 3, 5, and 7, and plotted the density transitions over time. First, when the threshold is set to 3, the system maintains a relatively stable density with only small fluctuations. In contrast, when the threshold is set to 5, the system reaches a stopping state earlier than in the other cases. However, the density shows larger fluctuations before stabilizing. Finally, when the threshold is set to 7, the density gradually decreases and stabilizes at a lower level compared to the other settings. Based on these results, we conclude that our threshold of 5 provides a good balance, and therefore we define the majority of neighbors as 5 in our model. However, as already shown in the density evolution figure, when the stopping probability of all cells reaches p equal 1, then the value is no longer changing, and the system comes to a complete halt. The snapshots on the right illustrate the system's states at 800,000 and 900,000 generations, showing that the configuration remains unchanged after convergence. So I'd like to introduce the second model, named as the twisted model. This model is based on the first model, but it differs in several key aspects. First, each cell can take one of two states, normal state or twisted state. When a cell is in twisted state, the stop rate P is updated differently from the pose model, as shown in the following equations. If many neighboring cells have performed update events while the cell itself has not updated, P is defined as 1 minus 1 divided by interval run. On the other hand, if many neighboring cells have not performed updates while the cell itself has updated, P is defined as 1 divided by interval pose. In this way, the twisted model introduces an alternative response to neighboring activity by modifying how the stop rate is calculated. Here I will explain the key difference in how the variable P is updated between the normal and twisted states. The variable P update in case of the normal state is shown in the left side. On the contrary, the update events relating the variable P in case of the twisted state is shown in the right, as you can see. From now, I'd like to explain the results of the twisted model. This figure shows the time evolution of the arrived cell density and the number of twisted cells over 1 million generations. At the beginning, both the density and the number of twisted cells rapidly decrease and then remain relatively stable for a long period. However, around the 750,000 generation, we observe a significant change. After this stagnant phase, the number of twisted cells suddenly increases. At the same time, the density also begins to fluctuate again, indicates that the system dynamics are reactivated. This result suggests that the introduction of a twisted series can trigger transition from a stable state to a more dynamic regime. Next, I will present the distribution of extinction impacts in the twisted model. In this analysis, we measure the number of consecutive generations during which the arrived density falls below a threshold of 0.075. Based on these measurements, we construct the frequency distribution of our extinction durations. As shown in this figure, the distribution follows the parallel behaviors. This type of scale-free distribution indicates that both small and large extinction events occur with a characteristic scale. Importantly, the observation of such scale-free behavior suggests the emergence of precarity in the system. This implies that the tested model may exhibit self-organized critical dynamics. Finally, I will show examples of the spatial distribution observed in the tested model. These two figures represent the system at the 800,000 and 900,000 generations. We can observe that some regions continue to evolve while others remain relatively static. This indicates that the system does not evolve uniformly across space. Instead, dynamic and inactive regions coexist within the same configuration. Such patterns suggest that even at the microscopic level, the system exhibits both regulatory and irregulatory. This coexistence reflects the complex dynamics introduced by the twisted model. And this is the conclusion page. Thank you for your listening.